You know what kills me about NASCAR's restrictor plate era? It wasn't the speed limits. It wasn't the pack racing. It was watching the smartest engineers in motorsports turn into outlaws. And nobody, I mean nobody, played that game better than the hollow bolt bandits of the late 1980s. Picture this. It's 1988. Daytona International Speedway. You're a crew chief watching your perfectly built 700 horsepower engine get neutered down to 450 horses because NASCAR slapped a restrictor plate between your carburetor and intake manifold. That aluminum plate with 4 tiny holes is literally choking your engine, the engineering equivalent of breathing through a straw while running a marathon. Your driver's out there in a 200-mile-per-hour traffic jam, and there's not a damn thing you can do about it. Or is there? This is legacy motoring, and I spend way too much time thinking about the engineering loopholes that changed motorsports forever. If you're someone who believes that innovation doesn't always follow the rules and that sometimes the simplest solutions are the most brilliant, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. This is the story of how one anonymous mechanic, whose identity remains protected to this day, discovered an engineering loophole so elegant, so simple, and so devastatingly effective that it took NASCAR years to figure out what was happening. We're talking about hollow bolts. 4 modified fasteners that turned also-rans into winners and made NASCAR's technical inspectors look like absolute fools. To understand why this trick was pure genius, we need to travel back to February 1987. Bill Elliott had just run 212.809 miles per hour at Talladega. Let that number sink in. A 3,400-pound stock car hitting speeds that made IndyCar look slow. Bobby Allison's crash that same year sent his car airborne into the catch fence, nearly taking out dozens of fans. NASCAR had 2 choices. Redesign every track in America or slow the cars down. They chose option 2. Enter the restrictor plate, a piece of aluminum roughly the size of a playing card, 1/16 of an inch thick with 4 precisely machined holes. Those holes measured exactly 29/64 of an inch in diameter for the superspeedways. The physics were brutally simple. Limit the air entering the engine, limit the power it can make. An engine needs 3 things to make power: fuel, air, and spark. Take away the air, and you've got an expensive noisemaker. But here's where it gets interesting. The restrictor plate bolted between the carburetor and intake manifold using 4 mounting bolts. Standard 5/16-inch bolt. Nothing special about them. NASCAR checked the plate's dimensions religiously. They used go-no-go gauges on the holes, they verified the thickness, they made sure teams weren't using trick plates that flexed under vacuum to open up the passages. They thought they had every angle covered. They were wrong. See, those mounting bolts passed right through the airflow path. The bolts themselves were inside the airstream between the carburetor and the engine. And that's when our anonymous genius had his eureka moment. What if the bolts weren't solid? The modification was beautifully simple. Take a standard mounting bolt, chuck it up in a lathe, drill a hole straight through the center starting from the threaded end. Stop just short of the head so it still looks normal from the top. You've now created a hollow tube that runs the entire length of the bolt inside the air passage. The walls of the bolt might only be 1/16 of an inch thick, but that hollow center creates a bypass channel. Now here's the engineering brilliance. 4 bolts, each with a 3/16-inch hollow center, gives you about 0.11 square inches of additional flow area. Doesn't sound like much, right? But when you're dealing with engines spinning 9,000 RPM trying to suck air through a restrictor plate, that extra flow is worth its weight in gold. Or in this case, horsepower. The teams running this setup figured they were getting an extra 15 to 25 horsepower. At Daytona and Talladega, where the draft keeps everyone bunched up, where races are decided by thousandths of a second, 20 horsepower might as well be 200. It's the difference between leading the pack and watching someone else's bumper all day. But wait, there's more. The really clever teams didn't stop at just drilling out the bolts. They experimented with different internal diameters. They tried tapering the holes wider at the bottom, narrower at the top to accelerate the airflow. Some teams allegedly experimented with rifling the inside of the bolts, creating a spiral that would spin the air as it passed through. The theory was that spinning air would maintain velocity as it entered the intake manifold, kind of like how a football spirals through the air more efficiently than one that wobbles. The carburetor spacer itself became part of the conspiracy. Teams would machine special pockets around the bolt holes, creating tiny plenums that helped direct air into the hollow bolts. From the outside, everything looked completely stock. The spacer was the right thickness, the bolts appeared normal, but inside it was a carefully orchestrated airflow management system. NASCAR's inspectors were going crazy. They knew something was up. Cars that should have been mid-pack runners were suddenly competing for wins. Qualifying speeds were higher than the math said they should be. During post-race inspection, they tear down the carburetors, measure the restrictor plates, check everything they could think of. All legal. The beauty of the hollow bolt trick was its invisibility. Unless you physically removed the bolt and looked at it from the bottom or cut it in half, you'd never know. And who's going to destroy a bolt during a routine inspection? NASCAR was checking dimensions, not doing metallurgical cross-sections. Think about the manufacturing precision required here. These weren't backyard mechanics with drill presses. Well, maybe some of them were, but the successful ones understood precision. The bolts had to be perfectly concentric. The walls had to be thin enough to maximize flow, but thick enough to handle the torque specs without crushing. Too thin, and the bolt collapses when you tighten it. Too thick, and you're not getting enough extra airflow to matter. The sweet spot was about 1/16 inch wall thickness, which required precise machining and high-quality steel. Some teams allegedly went even further. There were rumors of bolts made from exotic alloys, titanium or special steel compositions that allowed for even thinner walls while maintaining strength. The cost? Astronomical. We're talking about spending thousands of dollars on 4 bolts. But when a win at Daytona paid out $200,000 in 1988 money and sponsorship bonuses could double that, the investment made sense. The technical challenge extended beyond just making the bolts. Teams had to calibrate their entire engine package around this extra airflow. The carburetor jetting needed adjustment. The ignition timing curves had to be modified. The camshaft profiles that worked best with a restricted engine were different from what you'd run with that extra air. It was a complete systems engineering approach to, well, let's call it creative rule interpretation. Here's a number that'll blow your mind. Engineers calculated that at 7,000 RPM, those 4 hollow bolts were flowing an additional 50 cubic feet of air per minute. That's enough extra air to fill a phone booth every minute. In an engine where every cubic inch of airflow is fighting through that restrictor plate, that's massive. Look, the teams also discovered that the hollow bolt affected the air-fuel mixture distribution. The extra air coming through the bolts created turbulence in the intake manifold that actually improved cylinder-to-cylinder mixture distribution. So not only were they getting more air, they were getting better combustion efficiency. It was a double win. NASCAR finally caught on in 1991. The story goes that a disgruntled former crew member from one team tipped off NASCAR officials. He didn't just tell them about the trick, he brought them a cutaway bolt to prove it. Can you imagine being the NASCAR inspector who finally saw that? 3 years of wondering how these teams were beating the system, and it was right there under their noses the whole time. Literally in the bolts they were looking at during every inspection. The crackdown was swift and severe. NASCAR didn't just ban hollow bolts. They mandated that teams use specific bolts provided by NASCAR. These weren't just any bolts. They were specially manufactured with a unique head marking that couldn't be counterfeited. NASCAR would literally hand out sets of 4 bolts to each team before qualifying in races. After the race, those exact bolts had to be returned. They started serializing them, tracking them like nuclear material. But here's the thing about racers. Tell them they can't do something, and they'll find 3 new ways to do it better. When NASCAR started providing the bolts, teams tried everything. They attempted to drill out NASCAR's bolts and plug the tops with material that looked like solid steel but would vibrate out during the race. They experimented with special coatings that would burn away during the race, opening up passages. One team allegedly tried using a chemical treatment that would dissolve the center of the bolt over time, creating the hollow cavity during the race itself, like some kind of metallurgical time bomb. None of these follow-up tricks worked as well as the original hollow bolt concept. NASCAR had gotten wise. They started using different metallurgy for their bolts that would show obvious signs of tampering. They'd randomly swap bolts between teams. They'd weigh the bolts before and after races with scales accurate to 1/10 of a gram. The party was over. The hollow bolt era represents something bigger than just creative rule bending. It showcases the fundamental conflict between regulation and innovation in racing. NASCAR wanted close competition and safe speeds. Teams wanted to win. Engineers were caught in the middle, their creativity channeled into finding loopholes rather than advancing technology. Consider the engineering talent wasted on circumventing rules. The same minds that figured out hollow bolts could have been developing safer cars, more efficient engines, better aerodynamics. Instead, they were playing cat and mouse with the rulebook. It's the racing equivalent of hiring Einstein to do your taxes. Now you might be thinking that this was just cheating, plain and simple. And maybe you're right, but the restrictor plate itself became a masterclass in unintended consequences. NASCAR wanted to bunch up the field and create exciting racing. They got that, along with massive crashes that launched cars into the air. They wanted to level the playing field. Instead, they created an arms race of who could cheat most creatively. But let's talk about the engineering elegance of the hollow bolt solution for a moment, because this is where it gets really interesting. It didn't require any exotic technology. It didn't need computers or wind tunnels or million-dollar facilities. Just a good lathe, an understanding of fluid dynamics, and the courage to try something nobody had thought of before. It was accessibility meeting ingenuity, the kind of innovation that comes from desperation and brilliance colliding at 200 miles per hour. The trick also highlighted a fundamental principle of engineering that they don't teach you in school. The best solutions are often the simplest. While other teams were trying complex valve timing tricks or exotic fuel blends that skirted the rules, someone looked at 4 ordinary bolts and saw opportunity. That's not just smart racing, that's brilliant engineering. That's the kind of thinking that separates good mechanics from legendary ones. Modern NASCAR has learned from the hollow bolt era in ways that extend far beyond just checking fasteners. Today's inspection process uses tools that would seem like science fiction to 1980s inspectors. Coordinate measuring machines that can detect variations of thousandths of an inch. Ultrasonic testing that can find internal modifications without destroying parts. Chemical analysis that can detect non-standard materials. X-ray imaging that can see through solid metal. They've essentially built a forensic laboratory dedicated to catching cheaters, and that all traces back to 4 hollow bolts that embarrassed them for 3 years. The hollow bolt trick couldn't happen today with current inspection technology. Or could it? Racing engineers are still finding ways to bend rules. They're just more sophisticated now. Computer-controlled suspension components that change spring rates based on speed. Aerodynamic elements that flex at specific velocities in ways that are nearly impossible to detect with static measurement. Engine management systems that adjust power delivery based on track position or timing loops. The game continues, just with different rules and different tools. Here's what most people don't realize about the psychological impact of the hollow bolt era on NASCAR's entire inspection philosophy. Before 1991, NASCAR operated on a trust but verify system. They assumed teams were generally compliant and checked the obvious stuff. After the hollow bolts were discovered, that philosophy flipped completely. Now they assume everyone is cheating and work backward from there. Every single component is suspect. Every measurement is questioned. The relationship between NASCAR and its teams became fundamentally adversarial, and you can trace that shift directly back to 4 modified fasteners. The hollow bolt story also raises ethical questions about competition that still resonate today. Is creative interpretation of rules actually cheating, or is it innovation? If the rulebook doesn't specifically say bolts must be solid, is making them hollow wrong? These aren't just racing questions. They're the same dilemmas faced in business, technology, and life. Where's the line between clever and corrupt? Is exploiting a loophole the same as breaking a rule? Lawyers argue these points constantly. Tax accountants build careers on them. Racing teams just happen to do it at 200 miles per hour with millions of dollars on the line. For the teams that ran hollow bolts, it wasn't a moral question at all. It was survival. In NASCAR's top tier, the difference between first and 10th place could mean millions in sponsorship dollars, the difference between keeping your ride and losing it. When your livelihood depends on finding an edge, you find an edge. When your family's mortgage payment depends on your car being faster than the next guy's, you start looking at bolts differently. You start questioning every assumption. You start drilling holes in things. The anonymous mechanic who first drilled out those bolts has never been officially identified. There are rumors, of course, whispered names in garage areas, old-timers who claim they know exactly who it was, but nobody's ever stepped forward to claim credit publicly. Maybe because NASCAR's statute of limitations on rules violations is unclear. Maybe because the racing community protects its own secrets with the same intensity they protect their setups. Or maybe because the best treks are the ones where the magician never reveals himself, where the legend grows larger than any individual could support. What we do know is that between 1988 and 1991, hollow bolts were NASCAR's worst-kept secret, that somehow stayed secret from the only people who mattered, the inspectors. Crew chiefs would share knowing looks in the garage. Engineers would exchange subtle nods across the pit lane. Everyone knew somebody was doing it. Most suspected everyone was doing it. It was mutually assured destruction if anyone talked. The conspiracy of silence held for 3 years, which in racing terms is an eternity. The technical specifications of those modified bolts have become the stuff of legend, growing more impressive with each retelling. Some claim the best ones were gun-drilled to tolerances of plus or minus 1/100th of an inch, the kind of precision usually reserved for rifle barrels and surgical instruments. Others say teams experimented with electrical discharge machining to create perfectly smooth internal surfaces that maximize flow while minimizing turbulence. The truth is probably somewhere in between, but the mythology has grown with time. Every old mechanic has a story. Every retired crew chief knows someone who knew someone. Here's something that'll really bake your noodle if you think about it long enough. Engineers have retroactively calculated that if every car in the field was running hollow bolt with identical specifications, the competitive advantage would have been 0. Everyone would have had the same extra horsepower. The racing would have been exactly the same, just slightly faster overall. The only winners were the teams that figured it out first and kept the secret longest. And of course, the machinists making specialty bolts at premium prices. They did pretty well too. The hollow bolt trick also demonstrated the importance of tribal knowledge in racing, the kind of information that never gets written down anywhere. This wasn't something you'd find in any textbook or engineering manual. No university taught creative carburetor fastener modification. It was passed from mechanic to mechanic, team to team, a secret tradition of speed. The kind of knowledge that only exists in the minds and hands of people who live and breathe racing, who spend more time in garages than in their own homes. Today's NASCAR teams look back on the hollow bolt era with a mixture of nostalgia and amazement. Nostalgia for a time when a clever mechanic with a drill could outsmart million-dollar inspection procedures. Amazement that it took NASCAR so long to catch on, when the solution was literally bolted to the top of every engine. It's become a benchmark story, the one old-timers tell young engineers to illustrate that innovation isn't always about technology or money. Sometimes it's about seeing what everyone else overlooks. Sometimes it's about questioning assumptions that nobody else thinks to question. The physics behind why hollow bolts work so well deserves a deeper examination, because the science is actually fascinating. In fluid dynamics, there's something called the Venturi effect. As air accelerates through a restriction, its pressure drops. This pressure drop can actually help pull more air through adjacent passages, creating a sort of suction assistance. The hollow bolts created miniature Venturi tubes right next to the main restrictor plate holes. The interaction between these airflows created complex pressure gradients that further enhanced total flow beyond what simple area calculations would predict. It wasn't just about the extra area, though that mattered. It was about how that area influenced the entire airstream, how the bypass air mixed with the primary air, how the pressure differentials created favorable conditions for increased mass flow. Teams that ran computational fluid dynamics simulations years later with modern computers discovered something remarkable. The hollow bolt design was nearly optimal for its purpose, almost as if someone had done thousands of hours of computer modeling before creating it. But they hadn't. They couldn't have. The computing power simply didn't exist. The straight-through design, while appearing simple, created the least turbulence and maximum flow for the available space and constraints. Sometimes the first instinctive idea really is the best idea. Sometimes a mechanic's gut feeling about airflow beats a supercomputer's calculations. Or maybe that mechanic just understood air in a way that computers still struggle to replicate. The cost-benefit analysis is staggering when you break it down into real numbers. 4 custom bolts, maybe $2,000 in 1988 money, accounting for precision machining and the secrecy premium. Extra horsepower gained? 15 to 25, depending on execution. Cost per horsepower? Roughly $80 to $130. Compare that to traditional engine development, where teams might spend $50,000 or more to gain the same power through legitimate means, like better cylinder head porting or more exotic valve train components. The return on investment was astronomical. No wonder teams were willing to risk penalties. The math made the decision for them. But the real cost wasn't monetary. It was the breakdown of trust between NASCAR and its teams that persists to this day. The hollow bolt era contributed to an us versus them mentality that colors every interaction between competition officials and competitors. Every new rule is immediately analyzed for loopholes. Every inspection procedure is viewed as a challenge to overcome rather than a standard to meet. The relationship became adversarial rather than collaborative, suspicious rather than trusting. Some argue this dynamic was actually good for the sport, and there's merit to that position. The technical cat-and-mouse game created storylines that extended beyond just what happened on the track. Fans loved hearing about clever cheats almost as much as they loved watching races. It added a layer of intrigue to what could otherwise be just cars turning left for 3 hours. The hollow bolt story became part of NASCAR folklore, right up there with Junior Johnson's banana-shaped car that exploited aerodynamic loopholes, and Smokey Yunick's 7/8 scale Chevelle that somehow passed template inspection while being obviously undersized. The engineering legacy extends beyond racing into industries you might not expect. The hollow bolt concept has been adapted for legitimate uses in aerospace, where every gram matters. Engineers have used similar principles for weight reduction in non-critical fasteners on aircraft and spacecraft. Industrial designers have incorporated hollow structural elements in applications where both weight and airflow matter, like cooling systems for electronics or ventilation for industrial equipment. Sometimes racing's rule benders accidentally invent something genuinely useful. Sometimes cheating leads to innovation that benefits everyone. Let's put this in modern context, because the restrictor plate concept didn't die, it just evolved. Today's NASCAR Cup Series cars make about 670 horsepower unrestricted, around 510 horsepower with the tapered spacer at super speedways. That's still a massive restriction, roughly a 24% power reduction, but it's managed through precise fuel injection and electronic controls that would have seemed like magic to 1980s teams. The principle remains identical: limit the air to limit the power, but the execution is light years more sophisticated. The spacer is integrated into the throttle body. Sensors monitor everything. The ECU knows exactly how much air is entering the engine at any moment. Cheating is theoretically much harder now. The inspection process has evolved proportionally. Modern NASCAR inspection is a multi-million-dollar operation, involving laser scanning that creates complete three-dimensional models of every car surface, template grids that check hundreds of body points simultaneously, and enough measuring equipment to outfit a small engineering firm. Computer systems compare each car to a master CAD model, flagging any deviation greater than a few thousandths of an inch. The days of hiding modifications in plain sight are largely over, but teams still try. They have to. It's in their DNA. It's what they were hired to do. The hollow bolt story teaches us something fundamental about human nature that extends far beyond motorsports. Give people a constraint, and they'll find a way around it. Make a rule, and someone will find a loophole. It's not just about racing. It's about the unstoppable force of human creativity meeting the immovable object of regulation. Sometimes creativity wins, at least for a while. This dynamic plays out in every regulated industry, from finance to pharmaceuticals to professional sports. The hollow bolts just happen to be a particularly elegant example. For young engineers entering motorsports today, the hollow bolt era serves as both inspiration and warning. Inspiration that simple solutions can beat complex problems, that you don't always need the biggest budget to find the biggest advantage. Warning that getting caught can end careers and reputations, that the line between clever and criminal isn't always clear until you've crossed it. The mechanic who first drilled out those bolts probably thought he was just solving a problem, just doing his job, just trying to help his team win. He ended up creating a legend that's still discussed 35 years later. The technical details that have emerged over the years paint a picture of remarkable precision that rivals anything coming out of aerospace manufacturing facilities. The best hollow boats maintained wall thickness uniformity within 0.005 of an inch around the entire circumference, which meant the machinist had to account for material stress, heat expansion during the cutting process, and the natural inconsistencies in steel composition. The internal surface finish was polished to near mirror quality, reducing boundary layer friction to almost nothing. Some teams allegedly experimented with hydrophobic coatings on the internal surfaces, though the benefit at those air velocities was probably negligible. Still, they tried everything because leaving performance on the table wasn't an option. The most successful teams didn't just drill bolts and call it a day. They created entire integrated systems around those 4 fasteners. Custom carburetor spacers with carefully designed air passages that captured and directed airflow into the hollow bolt openings. Intake manifolds subtly modified to take advantage of the extra flow entering at those specific locations. Camshafts ground with profiles that utilize the additional air volume at specific RPM ranges where the hollow bolt effect was most pronounced. It was holistic engineering. Every component optimized around those 4 hollow bolts like they were the center of the universe, because for those teams, they basically were. The heat management challenges alone would have stopped lesser engineers cold. Those bolts weren't sitting in some temperature-controlled environment. They were sandwiched between a carburetor running fuel at ambient temperature and an intake manifold absorbing heat from an engine running at nearly 200 degrees. Thermal expansion could change the internal diameter of those hollow passages by measurable amounts during a race. Teams had to account for this, selecting materials and wall thicknesses that would maintain optimal flow characteristics, whether the engine was cold at the start or heat-soaked after 3 hours of racing. NASCAR's response to the hollow bolt scandal fundamentally changed how they wrote rules going forward, and this shift affected every aspect of Cup Series competition. Instead of saying what you couldn't do, which left room for interpretation, they started specifying exactly what you must do. Bolts must be solid throughout their entire length. Bolts must be sourced from this specific manufacturer with this specific part number. Bolts must have this exact weight within a tolerance of 2 grams. The rulebook went from general guidelines to encyclopedic specifications that read like engineering drawings. All because someone got creative with a drill press and a lathe. The cultural impact rippled through the entire sport in ways that persist today. The hollow bolt trick became a philosophical litmus test for how crew chiefs viewed their relationship with the rulebook. There were those who saw it as cheating, pure and simple, a violation of the spirit of competition that should be punished severely. And there were those who saw it as innovation within ambiguity, exploiting unclear language that NASCAR should have written better. That philosophical divide still exists in every racing paddock in the world, from Formula One to dirt track modifieds. Is it cheating if the rule doesn't specifically forbid it? Lawyers have argued this question for centuries. Racers just happen to argue it at higher speeds. In the end, the hollow bolt era lasted roughly 3 years. 36 months where 4 modified fasteners could transform a mid-pack car into a legitimate contender. In the 100-plus year history of automobile racing, it's barely a footnote chronologically. But for those who were there, who knew the secret, who watched inspectors tear apart carburetors while completely missing the obvious. It was everything. It was proof that brains could beat budgets, that clever thinking could overcome technological disadvantages, that David really could knock down Goliath with the right slingshot. The anonymous mechanic who started it all is out there somewhere. Maybe retired, maybe still consulting in the sport under the radar. Probably watching modern NASCAR with its tapered spacers and electronic fuel injection and computer-controlled everything. Probably chuckling every time commentators talk about teams pushing the envelope, because he knows what pushing the envelope really looks like. 4 bolts, hollow centers, 25 horsepower, and a secret that changed how an entire sport approaches technical inspection forever. When you think about American racing innovation, the big stories usually involve headline technologies. Overhead cams revolutionizing engine design, fuel injection replacing carburetors, ground effects transforming aerodynamics, carbon fiber reshaping structural engineering. But sometimes the greatest innovations aren't about what you add to a car. They're about what you take away. In this case, the center of 4 bolts, material that weighed maybe 2 ounces total. 2 ounces that were worth their weight in champagne and trophies and sponsorship checks. That's the beautiful paradox of the hollow bolt story that engineers still discuss today. The most elegant solution to NASCAR's restrictor plate rules was also the simplest. Not exotic materials requiring specialized supply chains, not complex mechanisms with failure points. Just the absence of metal where metal was expected to be. A void that became victory. Empty space that was worth everything. It's almost Zen in its simplicity, the idea that nothingness could be so valuable. The story also reveals something important about how sanctioning bodies evolve their enforcement capabilities over time. Before the hollow bolts, NASCAR's technical inspection was largely reactive. They'd find something suspicious, figure out how it worked, then write a rule against it. After the hollow bolts, they shifted toward predictive enforcement, trying to anticipate what teams might try before they tried it. They started hiring former crew chiefs specifically to think like cheaters, to imagine what loopholes existed and close them preemptively. The hollow bolt experience taught them that waiting until after the fact was too late. This shift toward predictive enforcement had unintended consequences of its own. The rulebook grew exponentially more complex, creating new ambiguities even as it closed old ones. Teams needed dedicated personnel just to interpret regulations, lawyers and engineers working together to parse language that read like tax code. The cost of competition increased as compliance became its own specialized discipline. Some argue this complexity actually benefited larger teams with more resources to dedicate to rulebook analysis, widening the gap between well-funded operations and smaller independents. The hollow bolts, in trying to level the playing field through clever innovation, may have ultimately tilted it further toward those with deeper pockets.
The psychological impact on inspectors deserves examination too. Imagine being the official who checked those bolts dozens of times without catching the modification. The embarrassment when the truth finally emerged must have been crushing. These weren't incompetent people, they were professionals doing their jobs according to established procedures. The procedures just never anticipated someone would hollow out fasteners. After 1991, NASCAR inspectors developed almost paranoid attention to detail, questioning everything, trusting nothing. That paranoia sometimes created friction with teams over completely legitimate components that just looked suspicious. The hollow bolt legacy was an inspection culture that assumed guilt until innocence was proven. Here's what most people don't realize about how close this secret came to staying buried forever. If that disgruntled crew member hadn't come forward with physical evidence, NASCAR might never have figured it out. They knew something was wrong. Qualifying speeds and race performances didn't match their models, but they couldn't identify the source. They were looking at fuel systems, ignition timing, aerodynamic tricks, everything except the fasteners holding the restrictor plate in place. The hollow bolt could have remained racing's greatest unsolved mystery, whispered about but never confirmed. The informant's motivation remains unclear decades later. Was it revenge against a former employer, frustration at being pushed out of the sport, genuine ethical concern about unfair competition, or simply money, since NASCAR reportedly paid substantial bounties for verified cheating information during that era? Whatever drove the decision to talk, it changed the sport permanently.
One person's choice to break the code of silence rewrote the rules of engagement between NASCAR and its competitors. The manufacturing network that supported hollow bolt production represents another fascinating subplot. These weren't parts you could order from a catalog or machine in a typical garage. The precision required meant involving outside specialists, machinists who can maintain tolerances and keep their mouths shut. The secrecy requirements must have added substantial cost, paying premium rates for discretion as much as skill. Some historians believe only a handful of machine shops around Charlotte knew how to make competition-grade hollow bolts, creating an underground economy within the racing community. Finding one of these shops was as valuable as finding the right engine builder or chassis specialist. The bolt material selection process itself demonstrated sophisticated engineering thinking. Standard hardware store bolts wouldn't work because the steel composition was unpredictable and often too brittle for thin wall applications. Teams needed high-strength alloy steel with known properties, material that could be machined precisely and would maintain structural integrity under racing conditions. Some allegedly sourced aircraft-grade fastener stock, which provided excellent strength-to-weight characteristics but required specialized tooling to work with. The supply chain for cheating required as much attention as a supply chain for legitimate parts.
Torque specifications presented unique challenges that revealed the depth of engineering analysis involved. A solid bolt tightens predictably because the material compression follows established formulas. A hollow bolt behaves differently, with the thin walls potentially deforming under high torque loads. Teams had to determine new torque specs empirically, testing repeatedly to find values that secured the carburetor assembly without collapsing the bolt passages. Too loose and you risk air leaks around the gasket surfaces. Too tight and you crush your expensive hollow bolts and eliminate the advantage you paid so much to create. The aerodynamic effects extended beyond simple airflow volume in ways that surprised even the engineers who designed the system. Wind tunnel testing conducted years later, after the secret was out, revealed that hollow bolt airflow created beneficial turbulence patterns in the intake manifold. This turbulence improved fuel atomization and distribution across all 8 cylinders, meaning power gains came from both increased air volume and improved combustion efficiency. The combination effect exceeded what either factor would produce alone, a synergy that nobody fully understood while it was happening. They just knew it worked better than expected. Fuel system calibration for hollow bolt engines required complete reconsideration of established jetting protocols. More air entering the engine demanded proportionally more fuel to maintain optimal air-fuel ratios. But the additional air entered at specific locations, through the bolt passages rather than the main throttle bores, creating localized rich and lean zones that varied with throttle position and engine speed. Carburetor tuning became incredibly complex, requiring extensive dyno testing to map the fuel delivery corrections needed throughout the operating range. Teams that simply drilled bolts without adjusting fueling left significant power on the table. The ignition timing implications were equally complex. More air and fuel means faster flame propagation, which means optimal spark timing shifts earlier relative to top dead center. But the changed mixture distribution meant individual cylinders experienced different combustion characteristics. Some teams experimented with distributors that provided different timing to different cylinders, though this added complexity and potential failure points. The safest approach was finding a compromise timing value that worked adequately across all cylinders, accepting some lost efficiency for reliability. Cooling system impacts emerged as an unexpected consequence of hollow bolt operation. The additional power generated additional heat, obvious in retrospect, but not always considered in the rush to find speed. Radiator capacity that was marginal with restricted power became inadequate with hollow bolt power levels. Some teams overheated during races, watching temperature gauges climb as their extra horsepower cooked their engines from within. The successful hollow bolt operations understood that the modification was just one piece of a comprehensive package that included enhanced cooling capacity. Oil system stress increased correspondingly with the additional power output. Bearings experienced higher loads. Valve train components worked harder. The hollow bolt horsepower multiplied stresses throughout the engine, accelerating wear and increasing failure probability.
Teams running hollow bolts needed stronger internals to survive, which meant additional cost and weight. The most successful operations calculated whether the net performance gain, after accounting for heavier internal components, still justified the modification. For most superspeedway applications, it did. Transmission and drivetrain considerations rounded out the system's engineering challenge. More horsepower meant more torque through the driveline, which meant stress concentrations at every connection point. Gear failures became more common among teams running hollow bolts, particularly in first and second gear where torque multiplication was highest. Some operations preemptively upgraded to stronger transmission components, while others simply accepted higher attrition rates as the cost of chasing victories. The data analysis capabilities of that era limited how precisely teams could optimize hollow bolt configurations. Without modern telemetry systems, engineers relied on stopwatches, driver feedback, and chassis dynamometer testing to evaluate changes. The iterative process of refining hollow bolt specifications, from initial dimensions through various internal surface treatments, must have consumed thousands of hours and substantial expense. Yet teams persisted because the competitive advantage justified the investment. Driver awareness varied significantly across teams running the hollow bolt package. Some crew chiefs told their drivers exactly what was happening, reasoning that understanding the car's characteristics helped extract maximum performance. Others kept drivers completely in the dark, either to maintain plausible deniability during post-race interviews, or simply because drivers didn't need to know. The drivers who did know carried the secret silently, never discussing it publicly, even decades after retirement. The competitive dynamics between teams running hollow bolts created fascinating game theory scenarios that played out over those 3 seasons. If you knew your competitor had the technology, you couldn't afford not to run it yourself. But if you developed it independently without knowing others had it, you gained temporary advantage until they caught up. Information asymmetry became as valuable as horsepower. Teams employed counterintelligence tactics, spreading misinformation about their engine programs while trying to gather intelligence about rivals. Crew chiefs would casually mention fictional modifications during garage conversations, knowing the information would spread and send competitors down dead-end development paths. The sponsorship implications added another layer of complexity to the hollow bolt decision. Major corporate sponsors invested millions, expecting their cars to compete cleanly within established rules. If word leaked that their team was running illegal modifications, the reputational damage could exceed any prize money gained. Some sponsors reportedly knew and tacitly approved, understanding that winning required pushing boundaries. Others remained deliberately uninformed, maintaining plausible deniability that protected the corporate brand. The relationship between competition departments and marketing departments became carefully managed theater. Track surface variations affected hollow bolt performance differently than standard restrictor plate setups, adding yet another variable to an already complex equation. Daytona's smoother asphalt allowed higher sustained speeds, where the additional horsepower translated directly to lap time improvement. Talladega's rougher surface created more aerodynamic drag variability, somewhat masking the hollow bolt advantage in raw speed, but amplifying it in draft positioning where throttle response mattered enormously. Teams learned to adjust their hollow bolt specifications for each track, sometimes running different internal diameters depending on the venue. Weather conditions introduced unpredictable elements that hollow bolt teams had to manage on race day. Air density changes with temperature and humidity, and denser air means more mass flow through both restrictor plates and hollow bolts. Hot summer races at Daytona might see different power gains than cooler spring events at Talladega. Teams that understood these relationships could optimize their carburetor calibrations morning of the race based on weather forecasts, extracting every possible advantage from conditions their competitors might not fully account for. The pit stop dynamics shifted subtly for hollow bolt teams as well. With more power available, these cars could afford slightly different pit strategy calculations. They could give up track position knowing they had the horsepower to recover it, or they could push fuel mileage strategies knowing their power advantage would remain constant regardless of fuel load. Crew chiefs incorporated the hollow bolt performance differential into their race strategy planning, creating integrated approaches that maximize the benefit of their illegal advantage. The qualifying versus race setup considerations revealed sophisticated understanding of when the hollow bolt advantage mattered most. Qualifying runs happened in clean air, where maximum power produced maximum speed directly. Race conditions involved drafting, where power differences manifested more subtly in acceleration out of corners and positioning within packs. Some teams reportedly ran more aggressive hollow bolt configurations for qualifying, accepting the risk of inspection, then swapped to more conservative setups for race day when scrutiny was highest. Post-race inspection avoidance became its own specialized skill set for hollow bolt teams. NASCAR randomly selected cars for teardown inspection after races, with winners and top finishers facing near certain selection. Teams developed a rapid bolt swapping procedures that could be executed in the chaos of victory lane celebrations. While cameras focused on drivers spraying champagne, crew members worked behind lifted hoods, replacing hollow bolts with standard fasteners before NASCAR officials began their formal inspection process. The timing window was narrow, the stakes enormous, and the coordination required was remarkable. The statistical anomalies that hollow bolts created in race results must have frustrated NASCAR analysts trying to understand competitive balance. Cars would show inexplicable speed gains at superspeedways while performing normally at other tracks. Qualifying positions wouldn't match race results in predictable patterns. The usual correlations between team budgets and finishing positions broke down at restrictor plate events specifically. Looking backward now, the data tells a clear story, but contemporary analysts lacked the context to interpret what they were seeing. The parts failure analysis that NASCAR conducted during this period inadvertently helped hollow bolt teams refine their techniques. When engines failed during races, NASCAR would sometimes examine debris to understand failure modes. This feedback loop ironically helped teams identify which hollow bolt specifications were pushing reliability too far. Failures that NASCAR attributed to normal restrictor plate stress were sometimes actually hollow bolt related, and teams learned from these incidents without NASCAR realizing the true cause. The multi-generational knowledge transfer that occurred as crew members moved between teams spread hollow bolt expertise throughout the garage. A machinist who learned the technique at one operation might later work for a competitor, bringing the knowledge with them. This diffusion ensured that the technology spread beyond its originating team, democratizing the advantage while simultaneously increasing the risk of exposure through more people knowing the secret. The retirement of key personnel who possessed hollow bolt knowledge created ongoing security concerns for teams that had run the technology. Former employees who felt mistreated might seek revenge through disclosure. Those facing financial difficulties might be tempted by bounty payments. Teams allegedly maintained relationships with former personnel specifically to reduce disclosure risk, providing consulting payments or other benefits that bought continued silence. The documentation practices around hollow bolt programs reflected their sensitive nature. Unlike legitimate engineering developments that generated detailed records for future reference, hollow bolt specifications existed primarily in the minds of a few trusted individuals. Written records meant evidence that could be discovered or stolen. This oral tradition approach to technical development was necessary for security, but created knowledge preservation challenges when key personnel departed. The ultimate lesson of the hollow bolt era transcends motorsports entirely and applies to any competitive endeavor governed by rules. Regulations create constraints, and constraints create incentives for innovation around those constraints. The same human creativity that produces legitimate technological advancement also produces sophisticated rule circumvention. The difference between innovation and cheating often comes down to whether the governing body anticipated a particular approach. The hollow bolt pioneers weren't more unethical than their competitors who followed the rules, they were simply more creative in their interpretation of ambiguous language. The legacy persists today in every inspection bay, every rulebook revision, every suspicious glance between crew chiefs who wonder what the other guy might be running. The hollow bolts are long gone, replaced by NASCAR-supplied fasteners and inspection procedures that would catch any similar attempt. But the spirit that created them lives on in every engineer who looks at a regulation and asks not just what it says, but what it doesn't say. That questioning mindset, that relentless search for competitive advantage, that willingness to see opportunity where others see only constraints, that's the true inheritance of the hollow bolt era. 4 empty spaces inside 4 ordinary-looking bolts changed everything about how racing polices itself. That's a legacy worth remembering.